Okay, let's begin with the today's practical, which is determination of the solid. So now, you should you should have learned in in the environmental engineering two theory that there are many of the contaminants that are present, and these contaminants result into the increased pollution load. And what we are saying in environmental engineering 2 theory is nothing about how to remove this pollutant, right? So we are no we get small idea about what these pollutants are, and then we are what we are getting to learn is how these pollutants are getting removed in the scientific manner, as well as just not the scientific manner. The subject that you are being taught is also the removal of this pollutant in the most efficient manner, right? No, the most efficient manner, when I say that, is the less amount of energy, less no less cost, less manpower. So all these technologies and all this no your conventional STP or the modified STPs are the result of the extreme research, and these extreme research are not just focused upon the removal of the pollutant. They are also focused upon what is the cost efficiency. No, they do the cost comparison per the energy required per MLD, as well as they also think of what is the land required per MLD, right? So all this the land required, manpower required per MLD. So is there a higher scope of automation into that? So all these technologies are tested on that particular basis, and then they are applied at various levels, right? So now what we are going to see in today's practical is determination of the quantity of one of the pollutant, and the very important pollutant is nothing but the solids, right? So solids get into the wastewater via various entries, right? So it can get enter from the household activities as well. For example, nowadays you use a face wash which consists of the activated carbon granules, right? So when you wash the face, there is some roughy texture, that you coarse texture that has been where you get on your hand and face, and because of that there is a rubbing action. So even that small particle is nothing but the solids, and that get entry into the this sewage or the wastewater, and that is that is to be removed somehow. Now, otherwise what will happen, that will get entry, and that is very serious. Even when we wash the utensils in which we had made the curry or the sabji, so what happens is that we wash that utensil, so the onion particles, some other the other substance that we use to make a curry, which are in the solid form, gets entry into the sewage. So there can be lot of ways by which the sewage the sewage will have these solids into it. There are multiple entries for these solids to get. For example, even nowadays we have combined drainage system, so the storm water will also get the storm water is getting connected, or it is moving towards your STP only. So storm water will wash out all the solids on the road surface, and via that the inorganic solids will get entry into the STP. So no, there are multiple entries. What I'm trying to tell, but these solids are to be removed, right? So solid is one of the pollutant which will have to remove, and which will eventually reduce the BOD and COD, right? So no, when we are removing these solids, eventually what will happen? We are moving towards achieving the targeted BOD and COD for the sewage disposal as recommended by the various agencies, right? So for example, if I have to have my COD for disposal as 250 mg per liter. So government has told me that if I'm disposing a treated wastewater, the COD should not be more than 250 mg per liter, right? But no, the reduction of this COD value from say like 450 to 250 requires lot of operation, and no, because the COD in itself is because of solids as well, right? So removal of these solids will also remove the COD load as well, right? So same way is with the BOD as well. So removal of the no removal of the solids will remove the BOD as well. Now, why I'm saying so is now you will be getting it in a few minutes when we'll be trying to discuss about these solids. Now, no, you sir, you'll be saying that, sir, you have talked about no BOD, you have talked about COD, and when we talked about BOD and COD, it is normally related with the removal of the organic, no, or a removal of the organic matter or removal of the organic pollutant. So how come this, no, solids are contributing for COD and BOD? So most of the solids that we have in the, most of the solids that we have in the what you can say in the wastewater or the sewage is nothing but the organic solids, right? So organic solids have the maximum content. So these solids, no, sir would have already told you that the percentage of the solids in the wastewater is very less. It is actually 0.01% only. But this was 0.1%. Solids are also very troublesome, and they can, they particularly have very large impact when we are dealing with their removal. So let's no, I'm going to share the screen, and we'll be starting with the practical session directly. So let's understand. No. Okay, you can tell me in chat section if my voice is clear, and if the no, if the PDF is visible or not. In the chat box, someone from you can tell me quickly about my voice and the visibility. Okay, audible and visible. Thank you. So now I'll be share. No, we'll be reading out these determination of solids, and let's check out what we understand through it and how the determination of the solids is being done. So introduction part: solids in water indicate the concentration of the organic and the inorganic constituents. So the organic fraction defines the pollution load of the wastewater, and the inorganic component determines its suitability for the irrigation or the fish culture. Now you'll have to understand the solids can be organic as well as the inorganic. So when we talk about this organic solids, no, with the organic solids is, no, they will be defining the pollution load of the wastewater. What is the pollution load? That is nothing but what is your BOD and COD, right? So your pollution load will be nothing but what is the BOD per no, BOD per mg per liter, and COD mg per liter. That is called as the pollution load of the wastewater. And while the inorganic solids, no, what is the significance of the inorganic solids? Inorganic, no, the water mainly is used for the irrigation purpose also. And if the inorganic solids are more, what will happen? That will affect the no the soil fertility, because what will happen, these small inorganic solids will take a space of the take the no they will be getting into the space in the agricultural soil, and because of that the soil fertility will get disturbed, as well as in the fish culture as well. No, fish culture, what will happen if the inorganic solids are not removed? The fish, particularly the fish culture that we that is nothing but the nurturing of the fish, that for the commercial activity that we do, will get affected. So you won't be getting good results, right? So it is not restricted to only these two activities. Now, no, particularly you can relate it to the your health as well. So we normally talk, no, when we have a good inorganic solid, no, when the inorganic solid content in our water is more, no, there are chances of getting a kidney, no, there are chances of having a kidney stone, right? So no, because of that also, no, मराठी मध्ये आपण त्याला क्षार म्हणतो, right? Dissolved inorganic solids, right? So your inorganic solids can be in the dissolved state also, and no, though all this the bore water or the groundwater which we have is, we say that it is it is particularly heavy water. And no, why so? Because it consists of lot of dissolved inorganic solids into it, and that can affect your health as well, right? So many of the industries, many of the industries also face problem if there is very high inorganic content in the dissolved format. For example, if I'm using a boiler, and no, the boiler will, if I'm having an industrial operation in which the water is to be boiled, and if it consists of a high inorganic salt, so what will happen? There will be a scaling effect, that is the deposition of the solids will be taking place. So all this is important. So when we talk of sewage, normally we have a very high organic content, right? And that defines the pollution load of the wastewater. Even the inorganic content is more, and that particularly maybe that is to be removed, because we'll have to make a water suitable for the irrigation, fish culture, or some other allied industrial activities as well. So what are the various forms of these solids? This chart is very, very important, and normally the examiner will be telling you to draw this chart as a test, right? So when you're facing the oral, so he'll be telling you to draw the entire this flow chart or the distributions of the total solid. So let's understand. It is very, very easy to understand. Just a matter of a few minutes, and you'll be able to understand this. So firstly, let's say that total solids, that is the solids in whole amount of solids that we have is nothing but the total solids. So this total solids can be divided into total suspended solids. A short form is TSS, and no, it can be distributed into total dissolved solid. The short form is TDS. So your total solids, that is we normally call as TS. So TS consists of your TSS and TDS, right? So these two solids are very, very important. Now, how these solids are defined? So these solids are defined depending upon what is the size of this. When we say that a solid is a suspended solid, so when we have the when we have the particle size more than 10 raised to minus 6 mm, we say that the particle is a suspended solid, right? So more than 10 raised to minus 6 mm. Nextly, when we say that it is a dissolved solid, or the solid will have a tendency to get dissolved, then the particle size is between 10 raised to minus 6 mm to 10 raised to minus 10 mm. So here it is very, very important to understand. No? So 10 raised to your 10 raised to minus 10 is the smaller value, and 10 raised to minus 6 is the bigger value. So this is the range, 10 raised to minus 6 mm to 10 raised to minus 10 mm. So if your particle size is less than this 10 raised to minus 6 mm to 10 raised to minus 10 or within the range of this particular thing, then the the particle has a tendency to get dissolved, right? So when we have particularly when we say that there are suspended particle, a suspended particle will have a tendency to get settled, or it will remain in suspension. So this suspended solid will either get settled or it will not get settled. So your total suspended solids are categorized into two heads. These are the settleable suspended solids, where the particle size is more than 10 raised to minus 2 mm, right? So if my particle size is more than 10 raised to minus 2 mm, then the particle is said that it is settleable suspended solid, right? And similarly, if my particle range is between 10 raised to minus 6 mm to 10 raised to minus 2 mm, it is said as non-settleable solids. So why so? No, particularly now that when I'm talking in terms of size, you would have understand that the size is the size is very, very important here. Now larger is the size. What listen properly. Larger is the size. Larger is the density of that particle. Larger is the weight of that particle. And if larger is the weight of the particle, it has the higher gravitational force. If it is having a higher gravitational force, it will be settling properly, right? I'm repeating my statement. If the particle size is more, it has higher weight. Because it has a higher weight, it has a higher gravitational force. And now because of the gravitational force, what will happen? The particle will settle. So for a particle to settle, your size of the particle should be on the higher side. So 10 raised to minus 2 mm, particularly is is of the bigger size than 10 raised to minus 6 mm. So it will be having the tendency to get settled. Another criteria of the particle to get settled here is about the specific gravity. So specific gravity of that particle should be more than 2.65. See, if the specific gravity of the particle is more than 2.65, it will have the tendency to get settled. So I have told you two criteria which will decide if the particle is settleable or not. The particle should have a higher, it should have the higher particle size. Because of that, there will be higher weight. And as there is higher weight, larger gravitational force will be exerted, and because of that, the particle will get settled, right? And again, one more criteria is that the particle should have the specific gravity more than 2.65. Then also the particle has a tendency to get settled. No, exactly opposite is the case with the non-settleable particles. Non-settleable particles have lesser particle size. because they have lesser particle size, the gravitational force exerted by them is negligible, and hence they do not settle and they remain in suspension, right? So this is very, very important, right? Now again, no, for non-settlable particles, other they will be non-settlable because their specific gravity is less than 2.65. Here it is more than 2.65. Here it is less than 2.65. Because of that, they will be remaining in the suspension, right? So I'm hoping that no, the criteria for no settling of these particles is very clear to you. So you would have no learned it in the grid chamber design and the PST design as well, right? So grid chamber, the grit is nothing but an inorganic solid, and it has a specific gravity more than 2.65. So because of that, what will happen? A grit will get removed in the grid chamber, right? So that is very, very important. You would have learned it. Similarly, in case of PST also, the particle who achieve a good settling velocity. Now settling velocity also, no, you would have designed your PST on the basis of the settling velocity, or you would have decided if the particle is going to settle or not on the basis of the settling velocity, right? So settling velocity is again the function of your gravitational force. Higher is the gravitational force, higher is the settling velocity. So we do not want a higher amount of horizontal velocity, because if there is the higher amount of horizontal velocity, the particle won't settle and it will no, it will be removed from that particular settling tank. But if it is having the higher settling velocity, what will happen? That the particle will settle very, very easily in that settling tank, right? So no, I'm hoping that this is clear, right? So let's move towards no settleable suspended solids. Let's understand its division. So settleable suspended solids further can be divided as volatile solids and fixed solids. So what are the volatile solids? Volatile solids are all organic settleable solids, and fixed solids are all inorganic settleable solids. So what is volatile solids? No, all those solids, no, particularly which undergo no, we under which undergo the what you can say change in their state after no application of fire, or they get utilized, are called as the volatile solids. For example, wood. Your wood is a volatile solid. Why so? Because when you heat the wood, what will happen? Lastly, only the ash is going to remain, right? So all those particular things will get get what you can say utilized. All the volatile matter or the organic matter in that wood will get utilized, and there will be they will be called as that matter will escape or will get utilized, and hence it is called as the volatile solid. Not in case of burning also, right? So we can even do decomposition of this wood or organic matter. So what is happening when we do decomposition? This organic matter get utilized, and these solids are the hence are called as the volatile solids, right? So they are not fixed solids, they are volatile solids. But your fixed solids are what, irrespective of providing heat or irrespective of doing decomposition, anaerobic digestion, these your solids are going to remain as it is. These are called as fixed solids. So I'll be giving you a best example. So if I take a piece of wood, and I particularly I weigh that particular piece of wood. So let's say that it is 2 kg, right? After I'm burning that 2 kg wood, and after that, what will happen? All that wood will get burned, and what will remain is the ash. Let's say that that ash is 200 gram. So now what is the quantity of the volatile solids? 2 kg minus 200 grams is equal to 1800 gram was the volatile solids. And what is that 200 gram? 200 gram which has remained is nothing but the fixed solids. So the ash that is going to remain is nothing but the fixed solids here. So I'm expecting that you have understood what is the difference between the volatile solids. So wood is a volatile solids, and your ash is nothing but the after burning, the ash that is getting generated is nothing but the fixed solids, right? Similarly, in non-settleable solids also there can be the category of the same thing, that is your volatile solids. Your volatile solids can be organic and non-settleable, and your fixed solids can be inorganic, non-settleable, right? So this particularly, I hope you are understanding this as well. So volatile solids and so your settleable solids can be settleable solids. Both your settleable and non-settleable solids can be defined or can be categorized as volatile solids and fixed solids. So here the difference, or what you can say here, the characterization remains same. Similarly, if you see of the total dissolved solids, so total dissolved solids can also be categorized as volatile solids and fixed solids. So volatile solids, particularly, it is the organic fraction, and the fixed solids normally will be your inorganic fraction, right? So I think that you have understood this particular this thing, and now if you have understood this, you have understood half of the practical of this. So this is very very important, right? And normally we when we go as an examiner, or when the examiner visits us, what he'll be asking us that he'll be asking you this particular classification as well, but he'll be asking you a question in which he'll be telling you where in from which unit you will be removing the total dissolved fixed solids. So total dissolved fixed solids will be getting removed from which of the unit of the STP. He'll be asking you the inorganic fixed settlable solids will be getting removed from which of the unit of the STP, right? So he may ask anything about this particular thing, and from where the solids are getting removed, from where the solids are getting removed. So all these different types of solids will be getting removed from one or the other unit. So you should be able to identify. For example, if you see the Great chamber, in Great chamber, what is happening? The Great is getting settled. The Great is inorganic in nature. So what is that particular Great? It is the fixed settlable solid. So the fixed settlable solid is getting removed in the Great chamber. Another thing, we have PST. Why PST is designed? PST is designed to settle the particles which are organic in nature and are having the higher specific gravity. So your volatile organic settlable solids will get removed here. The organic solids or the organic volatile solids will get removed in your PST, that is primary sedimentation tank. So this will be this should be particularly known to you, right? So now where this non-settlable solids will get removed. So now we see if you are remembering in WTP, that is water treatment plant, the non-settlable solids were getting removed in clariflocculator. So we were adding some coagulant, and with the help of the coagulant, what were happening? All the solids in the suspensions were getting removed. But in sewage treatment plant, we do not use any chemical except in the chlorination stage. So we do not use any chemical, right? Except in chlorination, when we'll have to do some, when we'll have to do disinfection, then only we are going to use chlorine or sodium hypochlorite as the disinfectant there. But apart from that, in entire your STP, we are not going to use chemical anywhere, right? So where this non-settlable solids will get removed then? That is the question. So that should be wisely answered, or you should be able to answer that. So if there is no chemical treatment that is to be done, there should be some treatment in which this non-settlable suspended solids or entire this this particular non-settlable suspended solids will get removed. So what is that particular unit? It is nothing but your secondary treatment unit. So secondary treatment unit, that is the biological that we have, that is the ASP, right? So ASP you must have now started with the aeration tank, and nextly the secondary sedimentation tank. So what will happen is that the organic volatile solids which are non-settlable will get converted into settlable organic solids in your aeration tank. So because of the redox reaction that is happening, because of the chemical oxidation and reduction reaction. So in aeration tank, you shouldn't be getting confused that the aeration tank is only used for supplying of the oxygen. Why we are supplying the oxygen? Because oxygen is an oxidizing agent. It will reduce the non-settlable suspended solids to settlable suspended solids, and then they will be getting removed in secondary sedimentation tank. Similarly, the redox reaction will also help the non-settlable fixed solids to get converted into settlable solids, and they will be getting settled in the secondary sedimentation tank, and they will be getting removed, right? So your non-settlable suspended solids will have to be turned into settlable solids where in the aeration tank because of the redox reaction, and then they will be getting settled into the secondary sedimentation tank. So this is the answer for where the non-settlable suspended solids will get removed. So they will be getting only removed by the redox reaction, which is happening in the aeration tank. And because of the redox reaction, they will be getting settled into, because they will be getting reduced. And because of that, they have, because of that, they'll be getting removed in your secondary sedimentation tank. Right, so we are converting their nature non-settlable to settlable in aeration tank and getting them removed in the secondary sedimentation tank. Similar is the case with your total dissolved solids. So total dissolved solids, if I'll have to remove, so I'll have to make this total dissolved solids again settlable, right? So same in the case of your aeration tank, what will happen, this total dissolved solids will undergo the redox reaction, right? So redox reaction will make them settlable, and these particular solids will get removed in the secondary sedimentation tank, right? So I'm hoping that I've made very clear, and this is the most important, important questions which will be asked by the examiner in your examination related to the solid. So I'm repeating again, volatile solids, settlable volatile solids will get removed in the PST. Fixed fixed solids, which are settlable inorganic solids, will get removed in your grit chamber. Non-settlable suspended solids will get removed in the secondary sedimentation tank because of the redox reaction happening in the aeration tank. And similarly, the total dissolved solids will get removed in the secondary sedimentation tank because of the redox reaction that is happening in the aeration tank, right? So this was the part of your theory, but I thought that I should explain this as well, because this is normally the favorite questions of the examiners as well. So why there is importance of the solid determination? Let's check that. So TS determination classifies the wastewater as weak, moderately strong, and strong. So depending upon what is the concentration of your total solids, we can classify your water or wastewater or sewage as weak. If your total solid concentration is around 350 mg per liter, we can say that the wastewater is moderately strong if the concentration is around 700 mg per liter, and we can say that the wastewater is strong, or sewage is strong when there is the solid concentration of around 1200 mg per liter. So depending upon the concentration, you can classify this wastewater. Similarly, the TSS, so I've already told you, TSS is nothing but the total suspended solids, determines the suitability of the wastewater effluents for disposal into the land surface or the water. So here we have very important TSS that is to be determined. There are some there are some rules and the standards that are set by the various agencies, and that defines if the wastewater is suitable for the disposal into inland surface. So inland surface will have lot of aquatic flora and fauna, and if the TSS is very large, that is the total suspended solids is very large, so what will happen, that the aquatic flora and fauna will get disturbed. Again, settlable solids determination indicates the efficiency of the primary sedimentation. Based on this, whether the primary sedimentation tank is required or not, and if required, detention time to be adopted for this PST designs are decided. So this is very interesting thing. Settlable suspended solid, right? So this particular fraction, settlable suspended solids. So if this particular solids are less, there is no chance in there is no requirement of your PST, right? So settlable suspended solids is less. So if you see the classification, so it has settlable organic, settlable organic settlable solids and inorganic settlable solids. So inorganic settlable solids are already getting removed in the grit chamber, and if already the settlable suspended solids are less, and from that some fraction is getting removed in the grit chamber. So particularly the fraction of your organic settlable solids which are getting removed in PST is very less. So you can directly skip PST. If you are directly skipping the PST, so imagine particularly imagine that how much cost you are going to get, you're going to avoid, right? So the cost of land and cost of energy and all those things will be getting avoided, right? So again, we can particularly skip this PST as well. But if the PST is to be provided, we have thought that if we have a good amount of settlable suspended solids. So with the help of the concentration of the settlable suspended solids, we can also determine what is the detention time of that PST, right? तो पीएसटी का डिटेंशन टाइम डिसाइड करने के लिए भी ये वाला जो कॉन्सेंट्रेशन है ना टीएसएस का, वो बहुत ज्यादा इंपॉर्टेंट हो जाता है। हम लोग एक एक्सपेरिमेंट देखने वाले हैं उसके लिए कि अगर सस्पेंड हमको सेटलेबल सॉलिड सेटलेबल सस्पेंडेड सॉलिड है, तो उससे हम लोग नो डिटेंशन टाइम कैसे डिसाइड कर सकते हैं पीएसटी के लिए। So let's no we'll be seeing that as well. So volatile solids, no volatile solids, that is the volatile settlable in solids, indicate the fraction of the organic loading of digesters contributed by primary sludge from PST. So as I've already told you that this particular fraction is going to get removed in the PST. So no that particularly primary sludge from PST कितना generate होगा वो क्या बताएगा आपको, कौन बता सकता है, उसका आइडिया आपको यहाँ पे मिलेगा। वोलाटाइल सॉलिड्स का कॉन्सेंट्रेशन से आपका that particular thing आपको पता चलेगा, राइट। तो नो दैट पर्टिकुलर नाउ दिस नो प्राइमरी स्लज का क्वांटिटी अगर हमको पता चल गया, तो आपको जो लास्ट में एनारोबिक डाइजेस्टर्स आपको तैयार करने टू हैंडल दिस प्राइमरी द स्लज फ्रॉम द पीएसटी एंड एसएसटी, उसका वॉल्यूम कितना डिसाइड करना है वो भी आपको कहां से पता चलेगा, यू विल बी गेटिंग टू नो इट फ्रॉम द वोलाटाइल सॉलिड्स concentration। non-settlable suspended solids, right, non-settlable volatile solids, dissolved volatile solids and dissolved fixed solids indicate the pollution load to be removed by secondary treatment। See, I have already told you, right, all these solids, मतलब कौन सा solids, ये वाले solids पूरे के पूरे और ये वाले पूरे के पूरे solids, ये कहाँ पे रिमूव होने वाले आपके secondary treatment, they are going to get removed in ASP plus SST, so that is nothing but your secondary treatment। So now the concentration of this, the concentration of this plus concentration of this plus concentration of this is nothing but the organic load or the pollution load, not organic load, it is the pollution load that will that is coming all this concentration. It will be very helpful for us to to get an idea about what is the pollution load of the pollution load that need to be handled by the secondary treatment, right? So I'm hoping that you are understanding this and you are with me, because these are some of the very interesting terms and terminologies that we are seeing here, right? So total dissolved solids, that is inorganic, indicate the suitability of the wastewater for irrigation and fish culture. So we've already seen this. So TDS is again important, inorganic. So it will be deciding what is the suitability of the wastewater for irrigation and fish culture. Total volatile solids, right, determination in surge is used for designing organic loading of the anaerobic digester and also their efficiency for VS reduction. So all these total volatile solids, this volatile solid, again this volatile solid, and this volatile solid is going to get are going to they are going to get treated in the anaerobic digester. So knowing about the concentration of this plus this plus this is very, very important to for the designing of the anaerobic digester, which are going to stabilize this sludge. Now again, very, very important thing, you'll have to remember the amount of the PST, the amount of the sludge that is going to get generated in PST is totally dependent upon this particular factor, that is the organic settlable solids, right? The amount of grit that is going to get removed in the grit chamber is nothing but it is totally dependent upon what is the concentration of the inorganic settlable solids. Now lastly, SST, the amount of the sludge that is going to get removed in the in the SST totally depends upon this plus this plus this plus this. So all this particular thing are very, very important. So all this plus this and this plus this will not tell you or give you an idea about the amount of sludge or the quantity of the sludge that is going to get generated in the secondary treatment, that is secondary sedimentation tank, SST. Now what are the standards that are recommended, right? So these are the standards that are recommended by the various agencies. Specifically here is the Bureau of Indian Standards, right? So sewage effluent to discharge into the inland surface water. So if I have to I have treated the sewage and I have to discharge it into now the inland surface water, for example river, lake, any water body, so which is on land. So I should have my TSS less than 30 mg per liter. So maximum permissible limit is 30 mg per liter. So I should have my I should have my TSS concentration less than 30 mg per liter. So that is according to BIS 4764. Again, if I have treated an industrial effluent and now I want that industrial effluent to discharge it into the inland surface water, so what they have said is that the TSS should be, particularly it should be less than 100 mg per liter. That is according to the BIS 2490. Very, very important, right? So even if I know, if I have an industrial effluent which I have treated and I have to discharge into the marine coastal areas, for example, sea, right? So in C, if I have to discharge, again the standard remains same. That is the TSS should be less than 100 mg per liter. That is according to BIS 7968. And if I am having an inland surface water, and that inland surface water is to be used for irrigation, so what is the what is the maximum permissible limit of TDS? My TDS should be always less than 2100 mg per liter. So that is for the inorganic inorganic TDS what they are talking about. So that is about BIS 2296, right? So it's very, very important. All other parameters are related with TSS only. So if I have to discharge the sewage industrial sample into industrial surface in inland surface water, so the parameter that it has been related with is TSS. And for all no for the irrigation use, I'll have to relate upon TDS, right? So this is how this standards are being done. Now the experimentation is very, very easy, right? So it is an experimentation, even a fifth, sixth, the student of fifth standard or 16th standard can do, but the results from the these experimentations are to be applied, and that requires an engineering mind. So what we have seen up till now here, this all is nothing but related with our syllabus, that is the engineering, right? So environmental engineering too. So let's see what is the principle. So solids are determined by the gravimetric analysis. So what is the gravimetric analysis? So no, I think no, you haven't heard this word first time. You must have heard if you are reading some research papers and all those particular things. Gravimetric is nothing but the related with the weight. That is not WET. It is WEIGHT. वजन. जे वजनावरती जे analysis होतं, त्या analysisला आपण काय म्हणतो? Gravimetric analysis. We are saying that that's the gravimetric analysis. So in case in gravimetric analysis, we normally take the weights of various samples, and on the basis of the gravimetric analysis, we find out what is the concentration of the various solids, right? So change in the weight is going to tell us what is the concentration of that particular solid. So how we are going to do the all these types of analysis in which the weight plays a very important role are called as gravimetric analysis, right? So here gravi stands for gravitational and metric stands for the measurement, right? So it is nothing but the measurement of the gravitational force. So what is the weight? Weight is nothing but a function of your gravitational force. So W is equal to mg, right? So here we have g as a gravitational acceleration. So that particular thing that has been utilized here to find out what are the different types of solids and their concentration. So how we can find out the total solids? It is very, very easy. I can take a wastewater sample which is of the known volume, right? So like 100 ml, right? So I've taken a 100 ml sample of wastewater, and I'll be evaporating that particular sample. So what will happen? All the water will get evaporated, and what are remaining are nothing but the solids, right? And all those solids are nothing but the total solid. So now here, which temperature I have to keep is very, very important, because if the temperature is very high, the volatile solids will burn out and will not have the volatile solids will get utilized, and the total solids weight that I will be getting will be wrong, right? So I'll have to think of a temperature and the duration in such a manner that all other solids, only the water is getting evaporated and all other solids are remaining intact. I'm hoping that you're getting this, and this is very, very important aspect, right? So dissolved solids in the same manner. If I have to find out what are the dissolved solids, the dissolved solids are determined by how we'll be determining the dissolved solids. So this is particular chart. This is the no, I have to find out total solid. So no, I will be taking for the known volume of wastewater sample and I'll be evaporating it, right? So the remaining solids are nothing but the total solids. Now I have to find out the total dissolved solids. So what I'll have to do is from the total, no, I'll be relying upon the, as these are the dissolved solids, I'll have to again rely upon evaporation method only. But before going for evaporation method, I will have to remove this suspended solids from them, and then I can, then I can remove then I can evaporate the remaining sample. So how this total suspended solids can be removed? The total suspended solids can be removed with the help of the filtration, right? So I'll be removing the total dissolved solids by filtering a known volume of the sample, so that my total suspended solids will get removed, and I'll be getting only the sample which consists of the dissolved solid. So I'll be evaporating, and then the residue that is there, that will be nothing but that will be your total dissolved solids. So how I can find out fixed solids? Now we already know that if some heat energy is provided to this volatile solids, they will get escape. So no, I'll be taking the wastewater sample, एंड फॉर जितना मैंने टोटल सॉलिड्स को हीट एनर्जी लगाया उससे तो उससे बहुत ज्यादा मैं क्या करूंगा, हीट एनर्जी लगाऊंगा, जिससे क्या हो जाएगा, ये वोलाटाइल सॉलिड्स क्या हो जाएंगे, एस्केप हो जाएंगे, और मुझे क्या मिलेगा लास्ट में, फिक्स सॉलिड्स मिलेगा, राइट? So same is the case with your other settlable solids also. Now when I have to find out what are the settlable solids, so settlable solids can be found out, particularly settlable solids are determined by allowing the coarse suspended solids with specific gravity greater than 1 to settle under the still conditions over a specific period of time. The settled sludge is evaporated to dryness and the residue is weighed to determine the efficiency of the sedimentation. So now if I have to find out only this particular amount, that is settlable suspended solids, मुझे ये करने, तो मैं क्या करूंगा, I'll be taking a wastewater sample and then I'll be keeping it for some time, and all the particles which have a tendency to get settled will get settled, and then I'll be evaporating the the residue. I'll be collecting the settled solids, I'll be evaporating them so that the water will get evaporated, and I'll be getting what is the settlable suspended solids concentration. So here particularly here, if you see, we'll be coming back to the few this upper pages afterward. So here what we require is we require crucibles. The crucibles will be crucibles are those vessels in which we are going to put the wastewater, and this crucibles can sustain a very high temperature for like 1000 degrees Celsius. Also this crucibles can sustain, and they won't get damaged. The crucibles also comes with the lid, right? So we are going to have 100 ml of measuring cylinder. We are going to take a filter paper. So which filter paper is to be taken? Wattman number 40 filter paper is to be taken. We are going to take a funnel for filtering purpose. We need an EMOF cone, right? For 1000 ml measuring cylinder. We require very importantly the hot air oven. The capacity of this hot air oven is 250 degrees Celsius. But we do not require that particular temperature at hot air oven. We require a temperature of 104 to 105 degrees Celsius. So only 105 degrees Celsius, if you adjust, is also enough for this. Then we require a muffle furnace, right? So for determination of the volatile solids, and the temperature that this muffle furnace can handle is like 1200 degrees Celsius. But we do not require 1200 degrees Celsius for our solids determination. We require, for finding out the fixed solids, we require the temperature as 550 degrees Celsius. So with this muffle furnace, we are going to achieve that temperature. And here with the case in the hot air oven, that particular temperature that we'll be achieving is 105 degrees Celsius. So here is the procedure of test total solids. So what we are going to do is weigh and clean an empty crucible, that is particularly the weight will be W1 gram. So take a measured volume of the wastewater sample, say 25 ml if the sample appears strong, 50 ml if it appears moderately strong, and 100 ml if it appears and evaporate to dry. 100 ml if it is weak. So if you particularly with the help of the visible inspection, if you see that there are a lot of solids, there are a lot of solids in the sample, so we'll have to take even if we take less sample, then also we are going to get good concentration of solids. So if you on the visible inspection get to know that no, it is moderately strong. So there are moderate solids in that particular sample. Even a 50 ml 50 ml liquid will be required. But if you get to know, no, particularly that no, it requires it has very less solids. For example, your drinking water, right? So the drinking water that comes at your home from municipal corporation, if you have that, so there are very less solids into it. But if I have to determine, anyways, if I have to determine what are the solid content into it, so I have to take 100 ml. So if the solids are appearing are less, more sample is required, because if we take less sample, then the amount of solids will be less, and there will be no big change in the weight that we require. So we require change in the weight, right? So that particularly because of that, no, the sample that we need to take is very important, right? So let's say that we have taken like 100 ml of sample, right? So what we are going to do is we are going to pour this 100 ml of sample into this empty crucible whose weight is W1 gram, right? After that, what we are going to do is we are going to keep it in the hot air oven at 103 degrees Celsius to 105 degrees Celsius, right? So now how much we have to know, for which how much duration we have to keep? No, we have to evaporate it to the dryness, right? For some of the some of the wastewater samples, even we'll have to keep it for 24 hours. So normally we need to keep it for 24 hours, and because of that, all the water will get evaporate, and what will happen is that we'll get a dry sample. So what will have, why this dry sample is there? Because this dry sample, so we'll be getting a dry sample. Now here in that, if you if you have a proper look to the crucible, what you'll be seeing is some of the solids are now into that particular in that particular crucible after you have removed it from the hot air oven. So these are nothing but the solids. So now what we have to weigh this crucible again. So that weight will be W2 gram, right? So W2 minus W1 gram will be the weight of the solid. So weight of that residue which is inside that crucible. So that will be W2 minus W1 gram. And now that particular how much sample we have taken? Sample we have taken was 100 ml, right? So that will be noted down here. And all this 1000 in ml by liter and 1000 mg by gram is is taken here. This particular figure is taken here to particularly make this to make this unit as mg per liter, right? So if you do this all this dimensional analysis, so you will be getting the unit as mg per liter, right? So just W2 minus W1 gram, right? So now I have to determine the total dissolved solids. So how I'll be taking, I'll be doing the determining the total dissolved solids. I'll be taking a new crucible. Let's say that crucible is name is B. Earlier we have taken the crucible A, right here. So we don't have to use that crucible again, right? So we'll be taking a new crucible, or we are going to wash this crucible properly. And now we have a new crucible whose empty weight is W3, right? So what we are going to do is now we are going to take 100 ml of sample again. We are going to take 100 ml sample, and then we are going to pass it through filter paper, right? So filter paper is Whatman filter paper number 40, and we are going to collect the filtrate, right? We are going to collect that particular filtrate in this crucible B, right? So what will happen is that now, because of the filtration process, the total suspended solids are getting removed, and in your in the filtrate that is now being collected in crucible B, you have only total dissolved solids. So from entire total solids, because of the filtration process, you have removed total suspended solids, and what you are going to get via filtrate is nothing but the water sample which has only total dissolved solids, right? So again we are going to put that crucible B into hot air oven, and we are going to keep it to 103 degrees Celsius, and till we achieve the complete dryness. Now what we are going to do is we are going to again weigh that particular crucible. Let's say that the weight is W4. So your W4 minus W3 will be the total dissolved solids that you have. The original sample volume of sample that we have taken is 100 ml, and this particular arrangement we have done to get a unit of mg per liter. So you will be getting TdS in mg per liter by doing this complete procedure here, right? Now if I have to find out what is the total suspended solids, right? So we have found out what is, we have found out here what is TS, right? We have found out what is TdS, right? We also know that TS is equal to TdS plus TSS. So we can use this particular formula to find out TSS. So what will be the TSS? It will be nothing but the total solid concentration minus the total dissolved solid concentration, right? So this is very, very important. No? So total suspended solid, we do not have some different technique to find out, right? So we have found out what is the total solids concentration. We have found out what is total dissolved solids concentration, and your TSS is nothing but TS minus TdS. Similarly, I can find out now total volatile solids. Now, what are the volatile solids? So, volatile solids are the solids which are particularly are able to escape when we give the heat energy, right? So now what we are going to do is, now here we are going to do some steps after this particular process. So we are going to use same this crucible A only. So the very first process in getting the value of T total volatile solids is that firstly find out what is total solids, right? So total solids we have used, particularly we have taken an empty crucible, we have weighed it W1 gram, we have taken 100 ml sample and we have put that 100 ml sample in this crucible. Then we have put it for by the hot air oven for 103 degree to 105 degrees Celsius, and we have again weighed, that is W2, right? So W2 minus W1 is going to give us the total solids. Now we are going to continue with the same crucible. We are not going to wash it, right? So same this W2, we are going to take the same crucible which has a W2 gram, and what we are going to do next is, see here we'll have to come here. So keep crucible A containing total solid residue in a muffle furnace. So W2 जो आपका crucible है उसको हम लोग क्या करेंगे, ये वाला जो आपका ये है, अभी तक हम लोग हॉट एयर ओवन में रख रहे थे, राइट? अभी हम लोग वही क्रूसिबल को क्या करेंगे, वेट करने के बाद हम लोग उसको we are going to keep it in the muffle furnace. Then we are going to adjust the temperature to 550 to 600 degrees Celsius, and we are going to keep that crucible at this particular temperature for half an hour. So what will happen, because of this particular very high temperature, this volatile matter will get escaped, and lastly you will be having an ash into this crucible A, right? So now we are going to determine what is the TVS. Now how come, what will be the TVS? Previously we have this W2 weight, so W2 and minus this W2 minus this, here should be W2, yeah, it is right. We are going to weigh that crucible which we are going to take out through the muffle furnace, that will be weighed as W5. So W2 minus W5 will be nothing but the amount of total volatile solids. So W2 was giving you an idea about the TS, but now W2 minus W5 will be giving you an idea about the TVS, that is mg per liter. We are going to keep an original sample, that is 100 ml here, and similarly we are going to find out TVS. Same way, if I have to find out TFS, instead of particularly here the formula will change, it will be W5. This is the W5, that is the weight of crucible plus ash, and W1, that is the empty weight of the crucible. So we are going to find out what is the weight of ash here with this W5 minus W1. Original sample was 100 ml, and this has been done to adjust the unit as mg per liter. So that will be getting you, they will be giving you the total fixed solids, right? So even you can find out particularly what are the total dissolved solids inorganic. So keep crucible B containing the dissolved solids. Here particularly you had this particular crucible where you stopped at this particular juncture. So after this W4 gram, you can keep this crucible B directly in the keep directly in the muffle furnace at 550 to 600 degrees Celsius for half an hour, and in that what will happen, all the all the volatile solids will dissolved volatile solids will get escaped, and you will be getting what are the total we will be getting what are the total dissolved fixed solids by using this particular formula, right? So all these particular formulas, I think you should go with, and you particularly should try with, with some numerical values. So we are going to do this via numerical values also. I'll be uploading this videos, and then you'll be understanding. Now I'll be taking you more. No, I'll be taking more 10 minutes of yours, and no, which will be which will make you answer the favorite question of your examiner regarding this total solids experimentation, right? So the favorite question of your examiner here is somewhere there which where we tried or no particularly, yeah, this settlable solids determination indicates the efficiency of the primary sedimentation. Based on this, whether the primary sedimentation is required or not, and if required, detention time to be adopted for PST design can be decided with the help of the settlable SS concentration, right? So now how this particular thing can be justified, I'll be telling you in the next 10 minutes, and then we'll be stopping in this particular practical session of today's, right? So here we have, during the total solids and total dissolved solids determination, a temperature of 103 degrees Celsius to 105 degrees Celsius is adopted for evaporating the solids to the dryness. Now, why this particular temperature has been adopted? Why the temperature of 103 degrees Celsius to 105 degrees Celsius is adopted for the total solids and total dissolved solids determination? Because at this temperature, only water content is getting lost, but no degradation and the loss of the weight of the solids would occur. So that is it is only going to evaporate the water, and the volatile solids will remain untouched, right? So this particular temperature is adopted because of that particular criteria. Now what will happen now for the total volatile solids? What we have done is that we have adopted a temperature of 550 to 600 degrees Celsius, right? So why this particularly why this temperature we have adopted? So heating solids to 500 to 600 degrees Celsius during volatile solid determination results in the total degradation and the loss of organic matter. So organic content is nothing but your volatile solid. So when you heat a particular sample at 550 degrees Celsius to 600 degrees Celsius, so all the organic content will get utilized, and what remaining will be inorganic fraction. But very important thing what I'm going to tell you, you cannot directly put water in muffle furnace at 550 to 600 degrees Celsius, right? Because it will be damaging the muffle furnace. Firstly, you will have to evaporate the water at 103 degrees Celsius to 105 degrees Celsius, and then that particular crucible you will have to put at 550 degrees Celsius to 600 degrees Celsius. Otherwise, there will be a very huge damage to your muffle furnace. So that is not at all accepted. So you'll have to firstly evaporate the water, and then only you can put it into at a very high temperature of 550 to 600 degrees Celsius. Now let's particularly this is now the experimentation, a very small experimentation that can be done to decide whether if the PST is required or not, and if required, what should be the detention time, right? So in Imhoff cone experiment, efficiency of suspended solids removal can be found out with this particular formula, that is the settled sediment, that is mg per liter. So that is nothing but the settlable solids in mg per liter into 100 divided by total suspended solids. So these are the settlable suspended solids upon total suspended solids into 100. So that will be nothing but the percentage that you will be getting a percentage, right? So ye settlable solids aapka, what is your TSS? It is settlable solids plus non-settlable solids, but we are going to consider only the settlable sediments in this particular. तो आपके टोटल सस्पेंडेड सॉलिड्स में सेटलेबल सेडिमेंट्स कितना है, उसके बेसिस पर हम लोग डिसाइड करेंगे whether we'll have to give the PST or not. Now the answer of this particular equation comes less than 40%. If efficiency is less than 40%, there is no need of providing an PST. So efficiency less than 40% tells us that the settlable sediments are very less, and hence we do not require a PST there, right? So if efficiency is between 40% to 60%, it is desirable to provide a PST. If efficiency is more than 60%, PST must be provided. So like 40 to 60%, if the efficiency is getting to more than 40%, normally it is desirable to provide a PST. More than 60%, then compulsorily you will have to provide a PST. Now let's do an experimentation in which what we have done is that particularly we have taken a sample, y1 sample, y2 sample, and y3 no yeah y1 sample. Okay, not y1 sample. Let's name this samples as sample 1. There are three samples: sample 1, sample 2, and sample 3. Right? This is nothing but the time. So what we are going to do is, now we are going to take an EMF cone. So this EMF cone is of 1000 ml and it looks like this. Right? So this is the EMF cone. Right? So in EMF cone, what we are going to do is, we are going to put a 1 liter of sample directly into this particular this thing. So imagine that there are three EMOF cones. Here you can see only two EMOF cones. These are plastic EMOF cones, and on that the 1 liter graduation marks are there, from starting from bottom to top. Your top at this particular juncture at top, you'll be having the 1 liter mark. So imagine that there are three EMOF cones, and we have put no three different samples into it, and we are going to note down the readings of this settleable. Here you can see, here it is the settleable fraction that is being there. So here this is all the supernatant. Here in this you have supernatant, here you have a supernatant, but this is the settleable solids here, right? So no, after every few minutes we are going to, after, let's say, after every 30 minutes we are going to determine how much is the reading of this settleable solids here. So let's do that. So imagine, like, this was sample 1, sample 2, and sample 3. So after like 0, for 0 minutes the reading was 0, 0, 0. After, let's say, 30 minutes, that is 0.5 hour, the settleable solids in the first was 1.3, in second EMF cone was 1, and in third was 0.6. Similarly, after 1 hour, the settleable solids in first EMF cone was 2.2, that is milliliter per liter. The unit is here. It is 1.7 in second and 1 in third. For after 1.5 hours, these are the readings, and after 2 hours, these are the readings. Right. So now this let's plot a graph. X, all this time being on the X scale, and all this concentrations of solids on your Y scale. So this graph will look something like this, right? So this is graph 1 for your sample 1, graph 2, or this is the curve 2 for your sample 2, and curve 3 for your sample 3. Here you have different times, that is from from 0 hours to 2 hours, and here is the concentration of the particularly settleable sludge or settleable solids. So now, let's see that, let's focus on your curve number 1, right? So that is graph 1. So graph 1 indicates that the sedimentation increases with the time continuously, but a maximum detention time of 2 hours may be provided for a PST, beyond which putrefaction of the settleable solid matter can cause problem before disposal. So here you are going to, from this particular graph, you get a two very important answers, right? So normally you would have wondered in the class, what is this? You have a PST. What is the role of PST? The role of the PST is to remove the settleable organic solids. So one of the answer is here, that the role of PST is to remove the settleable organic solids. And the second answer, what is the maximum detention time that we can keep for PST? So maximum detention time that we can keep for PST is 2 hours, because what will happen after 2 hours, the putrefaction process, that is the degradation process of this settled organic solids, can start, right? So after 2 hours, the maximum detention time that you can keep for PST is 2 hours. That is very, very important. Because why so? Because after 2 hours the putrefaction process will start. So here you can see, as your graph curve 1, you can see the curve 1, if you concentrate, the the solids are getting more and more settled as the time is increasing. But you cannot go on keeping the PST for an infinite time, right? So so the detention time that we have is, the detention time cannot be infinite. So the maximum detention time here is 2 hours, and after 2 hours the water is to be moved to the your aeration tank. So that is this particular case. And here in this graph 1, you can very evident that the particularly the PST is very useful. PST will be required because the solids concentration, the settleable solids concentration is continuously increasing. Similarly, if you concentrate upon graph 2, so graph 2 particularly indicates that the detention time of detention time of 1.5 hours may be adopted for primary sedimentation, beyond which PST size will be undesirable and uneconomical, as there will be no further sedimentation. So if you observe this particular thing, after after this particular, if you see 1.5 hours, 1.5 hours, so what is happening, the curve is remaining same, right? So if the curve is remaining same, what will have to know, there is no amount of solid. So यहाँ पे भी उतना ही solids है, 1.5 आवर्स पे भी उतना ही सॉलिड्स है, 2 आवर्स पे भी उतना ही सॉलिड्स है. मतलब क्या हो गया, जितना भी सॉलिड्स को सेटल होना था वो सॉलिड सेटल हो गया. So now the detention time that you should keep for this such type of sample is how much? It is 1.5 hours only, right? And lastly, very important, graph number 3. Now what, graph number 3 indicates that a detention time of 1 hour will be adequate for the primary sedimentation, right? So here also you can see the after 1 hour the solid concentration here is remaining same, here it is remaining same, and here it is remaining same. So here you can adopt a you can adopt a detention time of 1 hour in this particular case. So to find out the efficiency, you'll have to use this particular formula. Then you can decide whether the PST is required or not. And if the PST is required, you can find out the detention time by carrying out such such studies, and then they decide what is the detention time.
We are going to see the determination of the solids experimentation. So as we have seen in the theory part, we require the crucibles for the determination of the solids, and what we are going to do initially is that we are going to take the empty weights of the crucible, right? So the crucible A and B here will be used for the determination of the total solids, and the crucible C and D here will be used for the determination of the total dissolved solids. So what we have done is we have cleaned these crucibles, we have washed these crucibles, and we have dried it in oven, right? And then what we are going to do is we are going to take the empty weights of the crucible. So the empty weight of each of the crucible is to be noted. So I am going to note the empty weight of all these crucibles. So crucible A has an empty weight at 48.862 grams. Right? Even the unit is important. Right? Nextly, the empty weight of crucible B I am going to note down. In similar fashion, the empty weights of crucible C and D will be noted. Now the next step is that to put the sample in it, right? So we are going to start with crucible A and B, of which we are going to which we are going to use for the determination of the total solids. So what this what has been given in the manual, or what we had the discussion, was that that we require, we will have to put some sample into it, and we'll be evaporating that particular sample. We'll be evaporating the water from it, and the remaining part will be the solids, right? So what we are going to do is, we are going to put these samples into these crucibles. Now this sample, the quantity of the sample is to be decided upon the concentration of the solids into it. So approximately, if the solids are less, then we'll have to take 100 ml sample, right? If the solids are more, or we can say if the solids are moderate into that sample, we'll have to take 50 ml sample, and the solids are of a higher concentration, will be even the 25 ml of the sample is sufficient. So here we can see there is more number of solids into this sample, and what we are going to do hence is we are going to take only 25 ml of this sample. Now while taking the sample, we'll have to make sure that this is stirred properly, right? So we have a stirrer, and we are going to stir the solid properly, and then we are going to put this into the crucible, right? So 50 ml of this sample, right? So this 25 ml of this sample we are going to take. So as the solid concentration is more, I'm going to measure it here, right? It is 25 ml. comes out to be 25 ml. So I put it in crucible B. Similarly, I will be measuring the sample after stirring. 25 ml of sample is to be measured, and it will be put in the crucible A. Right? Now these are the samples which are ready for the determination of the total solids. Right? So we are going to perform the experimentation of the total dissolved solids as well. So I am going to take empty crucible for this, and for the total dissolved solids, what we require is we require the filtrate. We don't require the original sample. So if the original sample is taken, the suspended solids will be also be present here. So we are going to remove the suspended solids with the help of this filter paper. It is Whatman filter paper number 40. So it is to be properly folded in this manner. So I am going to fold this. It is a very easy fold. And after that, I will be making quarter fold for this. I will be putting this filter paper in this particular manner in the funnel. Right? Similarly, I am going to take this filter paper as well, and again quarter fold, and it will be put here properly. Right? Now what is to be done? Again 25 ml of the sample is to be passed through this filter paper, and it is to be collected in the crucible bin. Right? So I am going to measure 25 ml of sample, right? And I am going to put it in crucible C first, so you can see it properly how the sample is going to pass. Right? So I am going to put it here, just a small. Carefully, the sample is being put. Right? Slowly, what will happen is that the sample will get filtered through this filter paper, and the filtrate will get collected in this crucible below. The same procedure we are going to follow for the crucible D as well. So I am going to measure the 25 ml of sample. And I am going to pass it through the filter paper and collect the filtrate in the crucible D. Right? So we'll have to wait for a few minutes till this filtrate gets collected, and after that we'll be keeping these crucibles into the oven. Right? Okay, so we have finished with the filtration process. If you see the water, the sample that we have put is completely now got filtrated in this crucible C and D. So now what we are going to do, we are going to keep all these crucibles in the hot air oven. Right? So before that, let me start the oven as well. Right. So we are going to keep the crucibles properly. So crucible A and B is the crucible for total solids experimentation, and crucible C and D are the crucibles for the total dissolved solids experiment. Right? So all these 4 crucibles we have to keep in this hot air oven till all the water will get evaporated. So normally it requires 24 hours. Now the temperature is very important, right? So the temperature that we require for the water to evaporate and not interfere with the volatile solids is 103 to 105 degrees Celsius. So now here you can see, as we have now started the hot air oven, the temperature it is rising, it is 49.5 and it will be moving to 103.6 at maximum level. Right, so 103, why 103 to 105? We have already seen that at in this temperature range, or after 105 degrees Celsius, the volatile solids will start to particularly get utilized. So we don't want the volatile solids to get utilized. We only want the total solids and total dissolved solids, and hence we have kept this temperature 103, in the range of 103 to 105 degrees Celsius. So we are going to keep these crucibles for 24 hours, and then we are going to measure the final weight, and then we'll be calculating the total solids and total dissolved solids. Okay, so we have kept our samples for total solids determination and TDS sample before 24 hours in hot air oven at temperature, you can see, at 103.6 degrees Celsius. Right, so what we are going to do is, now we are going to remove the samples and take their final weights. So going to switch off this hot air oven, right, and we are going to keep this open for few minutes, right, and then one by one what we are going to do is we are going to remove this. Right, so what we have is the crucibles A, B, C and D. Right, so we can take out these crucibles with the help of the flange that we have, right, and we'll have to actually cool this crucibles for some time. Right. We normally keep this in desiccator, but we are not going to keep it in desiccator, and we are going to immediately take the weights of this crucibles. So we will be keeping them for some time to get cool, and then we are going to take their final weights. Right, so we have A, B, C and D crucibles with us, right. Okay, we have cooled the crucibles and we have transported it near our weighing balance. Right, so what we have to do is we have to just take the weights of all these crucibles. So I'll be telling you, I'll be only taking the weight of one crucible, likewise, and I'll be telling what are the different weights that we have recorded previously. So let's go with this C crucible, right? And the weight of this crucible is 50.195 grams, right? So similarly, we have previously taken the weights of all our crucibles A, B, C and D, right, and here you can see the weights have come in this manner. So for the total solids experimentation, the empty weight of the crucible A was this, and the final weight after the evaporation we have got this. Similarly for crucible B, it has been given. Same for the total dissolved solids, you can see crucible C empty weight and the final weight has been given, and the crucible D empty weight and final weight has been given. So now what next we are going to do is we are going to keep the total solids, the crucible of the total solids into the muffle furnace, right, and we are going to perform the experimentation for finding out the total volatile solids, right. Okay, so this equipment is called as the muffle furnace, and the muffle furnace will be used for finding out the total volatile solid. So what will happen is that what is the difference between your muffle furnace and hot air oven? The temperature that this can handle, that the muffle furnace can handle, is up to 1200 degrees Celsius, right? And here you cannot handle that particular temperature. Here it is restricted to 250 degrees Celsius only, right? And it can handle 1200 degrees Celsius. So in muffle furnace, just to evaporate the water, what we have done is we have kept the temperature slightly over 100 degrees Celsius, that was 103 degrees Celsius, and we have evaporated only water, and we haven't touched any form of solid. But here what we are going to do here is that from the total solids that we have got, we are going to evaporate the total dissolved solids. Evaporate, that means we are going to utilize the total volatile solids, and they will be getting utilized only when the heat is more, right? So heat that we are going to provide in this muffle furnace is 500 to 600 degrees Celsius, and we are going to keep this crucibles for half an hour, right? So these are the same crucibles that you can see, A and B, that we have done, used for total solids. And amongst this total solids that are present in this crucible, we are going to utilize the total volatile solids, right? So now the care we have to take, firstly, you don't have to switch on this muffle furnace immediately. What we are going to do is we are going to keep the crucibles first, and then we are going to start this muffle furnace. Now you have to remember, right, it is a very high temperature, around 550 degrees Celsius. So all that we have written here, that is the name of the crucible, like the crucible A and B here, that can also get erased. So what you have to remember is that how you have kept the crucibles, in what sequence you have kept the crucibles. That is very, very important. So what we are going to do is we are going to keep crucible number B first, right? We are going to keep the crucible number B first inside, and then we are going to keep crucible number A, right? Okay, you can see we have kept both the crucibles A and B. So these are the crucibles A and B that we have kept. So we are going to close this door, right? And we have to keep this notch open so that the required amount of oxygen goes inside. Once we start this crucible, we don't need to open this door. If we open this door, what will happen? There will be excess oxygen that will be getting supplied, and all this inside inside this muffle furnace, there will be the flames that will be taking place. Now we have to do the control. This is called as the controlled burning process, where the temperature is high. If we open the door midway, it will be uncontrolled. It will be happening in the uncontrolled manner. You can see lot of flames. So when we have kept the crucibles, now we are going to start this muffle furnace, right? So for starting the muffle furnace, I will just switch on the muffle furnace, right? So we have to keep our crucibles in this muffle furnace for. I'll be setting the temperature firstly. It is in the range of 550 to 600. So we are going to keep our temperature 550 only. It can handle the temperature of up to 1200 degrees Celsius. I'm going to keep it at 550 only. Okay, it is 550. I'll be setting this temperature. Now you can see the 550 is the set temperature and 26 is the current temperature. So it is heating. Yellow light indicates that it is heating in a small manner. And now we are going to keep it in half hour for 550. So it particularly will need to achieve 550 degrees Celsius. It will require 1 hour. It will require half an hour. And after that, for 550, when it is reached 550, then we are going to keep this crucibles here at for next 30 minutes. So total duration approximately is equal to 1 hour. So after 1 hour, we are going to remove this crucibles for the further calculation of the
volatile solids, right? Okay, so we have completed our first process. What we have done is we have removed the crucibles A and B. I've kept it in the same sequence, right? So this is our B crucible, this is our A crucible. It is yet to get cooled, right? So now what we are going to do is, in meanwhile, we are going to keep our crucible C and D, which are of TDS, right? So even for the TDS, we can find out what is the volatile content in that TDS, or what is the fixed content in that total dissolved solid. So what now we are going to do is, we'll be taking the weights of A and B crucibles after they are cooled. Meanwhile, we are going to keep the crucibles for of TDS for the further process in the muffled furnace, right? So the same thing we are going to do. Right? It is a bit hot. So what I am going to do is, I am going to place it with the help of the so at back side we have kept the crucible D, and this is our C crucible. Right, so both the crucibles we have kept properly. Right, and now we are going to start this muffled furnace and keep it these crucibles for 1 hour, sorry, for half an hour at 550 degrees Celsius, and after that we are also going to measure the weights, right? So what we'll be doing is, I'll be measuring we'll be measuring the weights at the same time. So let me start the muffled furnace. Right, so now it is 250 degrees Celsius inside temperature. It will rise to 550 degrees Celsius in like 15 to 20 minutes, and then at 550 degrees Celsius we have to keep these crucibles for half an hour, right?